Now we're going to do an example using the electrostatic force equation. The diagram to the right shows two metal spheres with charge of positive 1.0, and we got this little symbol right here. If you remember, that means micro. That's the SI prefix for micro, meaning times 10 to the negative sixth. So microcoulombs is positive 1.0 times 10 to the negative 6 coulombs. And negative 3.0 microcoulombs is negative 3.0 times 10 to the negative 6 coulombs, respectively, sitting on insulated stands. Now, this is important here, the insulating stands, because what that means a charge is fixed on that sphere because it's not allowed to leave. Insulating means that it doesn't allow electrons to move through it at all. So the electrostatic force between them, they're separated by 10 centimeters, which is 0.10 meters. In order to figure out the force, we need to use our electrostatic force equation. So it's going to be K times Q1 times Q2 divided by the distance between the two squared. That's 9 times 10 to the ninth times 1.0 times 10 to the negative 6 times negative 3.0 times 10 to the negative 6 times 0.10 squared, and that gives us a total force of negative 2.7 newtons. And remember that negative means attraction. And you can see that in the problem, because if we have a positive charge here and we have a negative charge here, then that means those two charges are going to attract each other. So to give us a negative force, which means attraction, mean that the force is in toward each other. Now, what direction is that? Well, it's inward, but if I'm talking about one charge or the other, let's say I'm talking about this positive 1.0 times 10 to the negative 6 coulomb charge here. What direction is attraction for that one? Well, it's going to be towards the other charge, so it's going to be to the right. But this other charge is going to have a force to the left. And that goes back to Newton's third law that every force has an equal and opposite force. So the 2.7 newtons that's going to be applied to the first charge is going to be to the right at 2.7 newtons, and the second charge is going to be to the left at 2.7 newtons. So they're equal but in opposite directions. So in your book, on page 552, number 9, it says a negative charge of negative 2.0 times 10 to the negative 4th coulombs and a positive charge of 8.0 times 10 to the negative 4th coulombs are separated by 0.30 meters. What's the force between these two charges? All right, so we got our electrostatic force equation. We'll go ahead and plug those numbers in. And we find that it's going to be negative 1.6 times 10 to the 4th newtons. That's about negative 16,000 newtons. And if you know that negative means attraction, that's going to be 16,000 newtons of attraction. So we get the electrostatic force is 1.6 times 10 to the negative 4th newtons of attraction. The Millikan oil drop experiment is actually the experiment that determined the actual charge of an electron. Basically what Millikan did is he had two plates here, one with a positive charge, the other with a negative charge that had an electrical field in between, and he sprayed oil droplets in there. Now, by spraying the oil droplets, what that does is that has friction between the oil droplets and the dropper itself and gives the oil droplets extra electrons, which gives them a charge. Now, when those electrically charged oil droplets go in between here, in this electric field, there's an electrical force that's going to be provided that is going to be upward. Now, gravity is also pulling those oil droplets down. So what Millikan did is he adjusted the electric field so that these oil droplets would actually hover in between. And when they were hovering in between, then he knew that the electrostatic force and the gravitational force were going to be balanced. Well, if he knows the density of the oil and how big the oil droplets are, he can actually determine the mass, which gives him the gravitational force. And then he can use the electrostatic force equation in order to determine how much charge it had. Now, with that being said, that only tells him the amount of charge. That doesn't give him the amount of charge of one electron. So what he does is he changes the electric field, decreases it so these oil droplets will actually drop down, and then another set with less electrons will come down and they will hover in between also. And he did that over and over and over again, allowing each layer to drop down and then another layer to hover. And then what he found is a difference between each one of the layers was this elementary charge, which is 1.6 times 10 to the negative 19th coulombs. So essentially what he found out is the difference between each layer was a difference of one electron, and that charge of an electron is 1.6 times 10 to the negative 19th coulombs. Now, the charge on a proton, since the number of protons and protons and electrons, when they're equal, the charges are going to be balanced, then that means a proton also has a charge of 1.6 times 10 to the negative 19. The proton is going to be positive and the electron is going to be negative. So let's use this electrostatic force equation with a hydrogen atom. We have proton that has a positive 1.6 times 10 to the negative 19th coulomb charge, and electron has a negative 1.6 times 10 to the negative 19th coulomb charge. And actually the width of a hydrogen atom is about 100 picometers, which is 1 times 10 to the negative 10th. This distance, this width of a hydrogen atom is referred to as an angstrom. So half of that would give us the radius of 5.0 times 10 to the negative 11th meters. We go ahead and plug in that into our electrostatic force equation. We get 9 times 10 to the 9 times 1.6 times 10 to the negative 19th times negative 1.6 times 10 to the negative 19th divided by 5.0 times 10 to the negative 11th squared. And that gives us a total force, electrostatic force of negative 9.2 times 10 to the negative 8th newtons. And since that negative is there, then that means it's going to be an attraction. So the proton and the electron are going to be attracting each other, which is good for atoms because we want that attraction in order for the electron to stay around the proton. Next one, we got a diagram that shows 3 metal spheres, one with a negative 40 microcoulomb charge, a positive 50 microcoulombs, and negative 30 microcoulombs respectively. The first and second spheres are separated by 2.0 meters, while the second and third spheres are separated by 1.5 meters. What's the total force on each sphere? In order to figure out the force on any sphere or anything, we got to take all the forces that we have and add them all together. Well, let's start between the first and the second sphere. In order to find the net force in the first one, we got to take the force between the first and the second. Then that's going to be, we know that we have a negative and a positive. That means they're going to attract. So the force on the first sphere is going to be to the right. Now the second sphere is going to have a force to the left that's equal, but we're not really concerned about that right now because we just want to figure out the force on the first sphere. So the force on the first sphere is going to be k times q1 times q2 divided by the distance between the two squared. So it's 9 times 10 to the 9 times negative 4.0 times 10 to the negative 5th. That's that 40 microcoulombs times 10 to the negative 5th. 5.0 times 10 to the negative 5th divided by 2.0 squared. We go ahead and crank that out and we get negative 4.5 newtons. Now that negative means attraction, and the direction for attraction on the first sphere is going to be to the right. So it's going to be 4.50 newtons to the right. The second sphere, the first and third sphere are going to apply a force on each other, and that's going to be equal to k times q1 times q3 divided by the distance between the two squared. So that's 9 times 10 to the 9 times negative 4 times 10 to the negative 5th times negative 3 times 10 to the negative 5th divided by 3.5, because we got 2 meters between the first and second, and then 1.5 meters between the second and third. So it's a total of 3.5 meters, and we go ahead and crank that out. We get a positive 0.88 newtons. Now it's positive, that means repulsion, and for the first sphere, repelling means away from the third sphere, so that's going to be to the left. So it's going to be positive positive 0.88 newtons to the left. Now that we've translated that over, we're going to add these two vectors together. We can kind of ignore the fact that it's an electrostatic problem. We're just going to add these two vectors. The 4.5 newtons to the right is going to be positive, and that 0.88 newtons to the left is going to be negative, and that gives us a total force of 3.62. And since this is positive and we've already translated over, it's going to be to the right, so 3.62 newtons to the right. On the second sphere, we have the same force, but in the opposite direction. So we've already figured this out. It's going to be 4.5 newtons, but it's going to be to the left because that's attracting toward the first. So we already know that one. Between the second and third sphere, that's going to be equal to k times q2 times q3 divided by the distance between the two squared. That's going to be 9 times 10 to the 9 times 5.0 times 10 to the negative 5th times negative 3.0 times 10 to the negative 5th divided by 1.5 squared. And that gives a total of negative 6.0 newtons. Now that negative means attraction, and attracting between for the second sphere toward the third sphere is going to be to the right. So we translate that over. It's going to be 6.00 newtons to the right. Now, since we've already translated over, we're going to take these two vectors and add them together. We got 6.0 newtons. It's going to be positive because it's to the right, and then the 4.5 newtons to the left. So that's going to be negative. We get a total of 1.50 newtons. So that's and since that's positive, that's going to be to the right, and that's the net force on charge 2. For charge 3, we have a force between 1 and 3. We already figured that out. It's going to be 0.88 newtons, and it's going to be to the right because these two charges, two negatives, are going to repel each other. So that's going to be away from charge 1, and that is to the right. Between 2 and 3, we've already figured out that force also. That's going to be 6.00 newtons, and that's going to be to the left because it's attracting. So we know that force and those forces. We're going to go ahead and add these two vectors together. The 0.88 is to the right, so it's going to be positive. The 6.00 is going to be to the left, so it's going to be negative, and that's going to be equal to negative 5.12 newtons, and that negative means to the left because we've already translated over from in or out to left or right. So the net force on charge 3 is going to be 5.12 newtons to the left. In the next example, it says sphere A is located at the origin and has a charge of 2.0 times 10 to the negative 6 coulombs. Sphere B is located at positive 0.6 meters on the x-axis and have a charge of negative 3.6 times 10 to the negative 6 coulombs. And sphere C is located at 0.80 meters on the x-axis, has a charge of positive 4.0 times 10 to the negative 6 coulombs. Determine the net force on sphere A. So we look at this diagram, and this is what the setup looks like. We go ahead and figure out the the net force on charge A, and the way we do that is we got to first figure out the force of each of the other charges on A. So we need to figure out the force between A and B. We go ahead and take K times QA times QB divided by the distance between the two squared. That's going to give us 9 times 10 to the 9 times 2.0 times 10 to the negative 6 times negative 3.6 times 10 to the negative 6 divided by 0.6 squared. And that gives us negative 0.18 newtons. Now, that means attraction between A and B, but for A, what direction is that? That's going to be to the right. So the force between A and B is going to be 0.18 newtons, and charge A is going to be attracted to the right towards charge B. Now for charge A and C, we have K times QA times QC divided by the distance between the two squared, 9 times 10 to the 9 times 2.0 times 10 to the negative 6 times 4.0 times 10 to the negative 6 divided by 0.8 squared. Punch that in your calculator, we get 0.1125 newtons. That's positive, which means repulsion, and repelling A is going to be away from charge C, which is going to be to the left. So it's 0.1125 newtons to the left. So we've used our equation. We actually translated it over already. And now we're going to use these two forces and add these two forces together. So we can ignore the fact that it's an electrostatic problem, just take these two forces and add them together. So we got force on A is going to be 0.18 newtons minus 0.1125, because the 0.1125 was to the left, the 0.18 was to the right. And we figure out that our answer is going to be positive 0.0675 newtons, which is going to be to the right because it's positive.